The first director of my office at DARPA was J.C.R. Licklider, who said in 1960, human brains and computing machines will be coupled together very tightly, and the resulting partnership will think as no human brain has ever thought. I see my talk today as a progress report on the human-machine symbiosis, or Symbiosis Homo et Machina, as envisioned by Licklider. Modern humans belong to the genus Homo. And over the centuries, thinkers have posited a number of names for the species. Ludens, the player; Socius, the social being; Sapiens, the wise or knowing one; Faber, the toolmaker; Religiosus, the religious one. Arguments can be made for each one of these names, but Homo sapiens has long been recognized as the way we talk about ourselves. Sapiens captures the essence of Homo sapiens. Sapiens is a hierarchy spanning data to wisdom, where data is the raw material of the sensory experience of the world around us. Information is the facts derived from data, the who, what, where, when. Knowledge is how these facts relate to each other. Understanding addresses the human need for explanation, and wisdom is sound judgment leading to actions to achieve desired goals. In the beginning, humans handled all tasks across the data-wisdom spectrum. With the advent of machines, we recognized how they could help us do things faster, better, cheaper than by ourselves. We started with machines performing low-level data and information processing tasks, freeing humans to concentrate on higher-level endeavors involving knowledge, understanding, and wisdom. The movie, The Imitation Game, actually provides a very great example of a machine being able to perform a data processing function beyond the ability of humans. For those of you who haven't seen the movie, it focuses on the noted British scientist Alan Turing, who during World War II successfully built a computer to crack the German code machine Enigma. Unlike his colleagues, Turing saw clearly the futility of trying to break the code by hand, and instead concentrated on constructing a computer to help. I say help because the computer could not do it all alone. Only the human members of the team could provide the insight on a critical common characteristic to each encrypted message, which gave a critical clue on how to decode these messages. Now, we've come a long way since the 1940s and Turing's computer built from bulky electromechanical relays. The chart here is an expression of Moore's law, which shows the exponential increase or logarithmic increase in the cost efficiencies for processing, memory, and hard disk storage. If we look at the blue dots for processing cost efficiency, we see that we've gone from about $1 trillion per million instructions per second in the 1940s, essentially an impossible task, to $1 per million instructions per second in the 2000s. This 12 order of magnitude jump, or trillion-fold increase in processing cost efficiency over 6 decades, continues to drive the explosion of information technologies around us today. This exponential growth in cost efficiencies has played a critical role in making it possible for machines to advance further up the data wisdom ladder. One important rung on this ladder is the knowledge of driving, as expressed in self-driving vehicles using a form of artificial intelligence known as machine learning. 3 DARPA events, Grand Challenges 1 and 2 and the Urban Challenge, held over 10 years ago during 2004 to 2007, played very pivotal roles in accelerating the development of self-driving vehicles using machine learning. The progress from challenge to challenge was truly spectacular. In the first challenge, no self-driving vehicle got further than a few miles and had some mishaps that we see here on the left image. But a little more than a year later in the second Grand Challenge, 5 self-driving vehicles finished a very challenging 132-mile course in the Nevada desert. And the winner is shown here from Stanford in the center image. And finally, in the Urban Challenge, 6 self-driving vehicles completed a complex 60-mile urban course that included traffic for the first time. And this was not only traffic between the self-driving vehicles themselves, as shown on the right, but also traffic provided by Hollywood stunt drivers in leased vehicles. Well, there's been a lot of progress in self-driving vehicles since 2007. And today we have Google's self-driving car, among others. Many of the individuals who are leading efforts today to develop self-driving vehicles competed in the DARPA challenges more than 10 years ago. 2 well-known commercial applications of machine learning are voice recognition on the left, featuring Siri, and face recognition by cameras on the right. Siri actually is the direct result of major investment by DARPA in AI over 10 years ago through a program called Personalized Assistant That Learns, or PAL. Now, recognition based on machine learning is not foolproof. Here, the computer is wrong in describing the image of the child. The boy is not holding a baseball bat. Individual correctness is critical in certain situations, such as whether that person running towards you is carrying a weapon or perhaps something much more benign. Now, the Department of Defense often finds itself in those types of situations. Machine learning based on deep neural networks for image classification is vulnerable to small perturbations of the physical object in question. For example, we show here that stickers placed in particular positions on a real stop sign can result in the image classifier misinterpreting the stop sign as a 45-mile-per-hour speed limit. This misinterpretation persists even as the vehicle approaches the stop sign. Instead of braking, the vehicle could accelerate with potentially disastrous consequences. So the 2 prior charts really highlight the important question of trust in the machine. This includes trust in the data, trust in the software, trust in the devices and systems that run the software. I will now describe a few programs from my office that really address this multifaceted challenge of trust. Consumer imaging products, such as smartphones, have become ubiquitous, and it is estimated that about 2 billion images and videos are uploaded daily to social media. Now, at the same time, a growing proportion of this visual media has been manipulated. Now, many manipulations are benign, done for fun or for artistic value, but some are for adversarial purposes, such as propaganda or disinformation campaigns. The forensic tools used today to detect manipulation lack scalability and robustness and addressed only a few aspects of media authentication. A complete end-to-end system for automated forensic analysis does not exist. So we started the Media Forensics Program, or Metaphor, to level this playing field, which currently favors the image manipulator, by developing technologies for the automated assessment of the integrity of images and videos. These technologies include the detection of pixel-level inconsistencies, as really shown here in the 2 images on this chart. We have a program called Brandeis that seeks to enable safe and predictable sharing of data in which privacy is preserved. Louis Brandeis is the inspiration for the name of the program, and Louis was a former Supreme Court justice, as well as the writer of a seminal paper on the right to privacy. The program is developing the technical means to protect the private and proprietary information of individuals and enterprises. The vision of the program is to A, maintain privacy, and B, tap the huge value of data. And really, rather than trying to strike some balance between these two, we seek a third option as shown in the chart, where data can be shared safely and predictably while preserving privacy. The potential impact of this program is tremendous. Assured data privacy would potentially help open the door to personal medicine as one notable example. We would like to acquire software in a manner similar to the way we do most other things. Consider the purchase of an umbrella. I go to a store. I select a few umbrellas. I open and close them to check them out. I like the navy blue umbrella with white reflective trim, but I notice there's a hole in the fabric. Well, I ask for another because I don't want a leaky umbrella. And one is brought to me without defects rather quickly. Well, now imagine if I was told that all umbrellas made by that manufacturer leak, but in a week I'll get a patch that I can repair the leak. And furthermore, there'll be future leaks requiring new patches. Well, I would guess that most of you would find this totally unacceptable and go look for umbrellas made by a different manufacturer. Unfortunately, all, and I emphasize all software, already comes with defects or vulnerabilities, and we accept a continual cycle of patching. We want to stop and get away from this paradigm. And toward that end, we have a couple of programs using formal methods to ensure that software is built as specified, that it is correct by construction. Software that does what it's specified to do and nothing else helps tremendously in hardening the software against cyber attack. We are developing tools and technologies for code construction, using formal methods for embedded software such as that in the mission computer for a helicopter. And in this particular case, we harden using formal methods the operating system and 2 control modules. We then left unprotected the software for the camera module, gave this unprotected software to a red team, and then challenged them to break out of that module into the rest of the system. Now, we had proven using formal methods that one cannot break out, and indeed the red team could not do so, certainly upholding the power of mathematics. Now, for those of you who are familiar with formal methods, you are aware of the fact that it's difficult to scale these methods to larger and more complex software programs. We have a program called Cyber Assured Systems Engineering, which really looks to overcome this challenge through the composability of formally verified software modules. Well, despite our best efforts at hardening software, these attackers do get in, and so we use automation to engage them in machine time rather than human time. One program that epitomizes this approach is the Cyber Grand Challenge, with the objective of automating what human hacker teams do in DEF CON's Capture the Flag competition, which is the world's premier tournament for computer hackers. The automation developed by the challenge includes the discovery and patching of software vulnerabilities. Each of the 7 final teams in the challenge, as represented here in this chart by the 7 high-performance computing systems, developed software-based cyber reasoning systems that went head-to-head in the world's first machine versus machine cyber competition held at the beginning of DEF CON in 2016 in Las Vegas. It was a great success. The first prize of $2 million was won by a startup from Carnegie Mellon University. The second prize of $1 million went to a team composed of the company Grammatech and a group from the University of Virginia. And third prize of $750,000 was won by a team from the University of California at Santa Barbara. A major highlight of the event was that software flaws can last minutes instead of as long as years. For example, one of the cyber reasoning systems discovered a software vulnerability actually unknown to humans in one of the rounds of the competition, and then 3 rounds later, a second system uploaded a patch with an elapsed time of only 15 minutes. I can't emphasize enough how much this automation is a game changer in strengthening the cyber resiliency of software. Essential to the advancement of autonomous vehicles is the collection of data generated by driving many, many, many miles. For example, Waymo's fleet of self-driving vehicles has collectively driven over 4 million miles over the period of 2009 to 2017. Now, this is an impressive achievement, but actually it's only about 0.1% of the 320 trillion miles driven on all U.S. roads during that time period. Developers look to close this gap by constructing models derived from the physical miles driven and then using these models in simulations involving thousands of virtual vehicles, driving billions of virtual miles. The combination of physical and virtual miles driven reaches the point where the remaining risk can be mitigated by buying insurance. Now, the Department of Defense has many missions requiring very strong assurance of the safety and formal correctness of the system, but for which no insurance can be purchased. And so we started the Assured Autonomy program to create technologies for the continual assurance of autonomous systems, where continual assurance is the assurance of the safety and functional correctness of the system, provided provisionally in design, and then continually monitored, updated, and evaluated during operation as the system and its environment evolve. The Internet of Things, or IoT, is projected to grow to billions of devices. By their low-cost nature, there are limitations on what can be done to protect these devices against cyber attack. Our Leveraging the Analog Domain for Security, or LADS program, is working to protect these IoT devices. So as a start, you might just want to recall that when software runs on physical hardware, that physical or analog signals can be generated, such as electromagnetic emissions, acoustic emanations, power fluctuations, thermal variations. And so the idea of LADS is that when software runs on physical hardware, there is a collection of analog signals that can be used to characterize the state of the software. So there's a set of signals for normal operation. But then if there's some kind of change, let's say due to a malicious cyber attack, in the software, we should see that reflected in a change in its collection of signals. And thereby we can use this as a cue for further investigation. So I hope I've given you a sense of what we're doing to help build trust in the data, in the software, and in the devices and systems running the software. Now, IoT devices will contribute to the generation of much more data and will help propel us into the zettabyte era. I use an exabyte as my unit of choice on this chart because it's difficult to fit the 21 zeros associated with a zettabyte while still keeping the font large enough to read. And it's worth noting with such data, we really have to look closely at the challenge of whether we move it to a centralized data center or do we keep it in place and operate it on it there. And we have developed actually a new program called Dispersed Computing to look at how we take advantage of local computing resources to solve this problem. And just to underscore the importance and the challenge associated with moving data, let's just look at 100 terabytes, which is a fraction of an exabyte, and of course even smaller fraction of a zettabyte. At 100 terabytes with 100 megabits per second, it will take about 100 days to move that from one place to another. So I think you can appreciate the importance of seeing what we can do with such large amounts of data locally to the data itself. And so in essence, the concept here is how can we make the network itself the cloud? So that addresses aspects of the movement of data. It's also worth emphasizing that given such massive data sets, that spurious correlations and many spurious correlations are inevitable, which really underscores the importance of moving from correlative analytics to causal explanatory models. And for humans, an explanation is usually needed before we feel we understand. So not coincidentally, machines are moving further up the data wisdom ladder to encompass understanding. And we are beginning to look more deeply into the automated generation of causal explanatory models from data, information, and knowledge. Our Explainable AI program is developing a new generation of machine learning techniques that are able to provide a rationale that explains conclusions that are reached by the machine learning system. And that's what's really illustrated here in this particular chart. Now, if current trends continue, future autonomous systems will need to perform increasingly complex and sensitive missions, and machine learning AI will be a critical part of these systems. However, if developers, users, and senior leaders are to feel confident enough to deploy and use AI-aided systems, then these systems must explain their rationale, and their recommendations, decisions, and actions must be delivered in a manner that human users understand and trust. Today, most machine learning systems provide no explanations, or the explanations they do provide are too detailed and at the wrong level of abstraction. This program will develop the tools needed to build explainable AI systems. So now let's just shift gears and envision a machine able to automatically transform data, knowledge, information into relevant causal explanatory models. Our Big Mechanism program is developing technologies that are making it possible to read thousands of research abstracts and papers, extract pieces of causal mechanisms from these papers, assemble these pieces into more complete causal models, and then reason over these models to provide explanations. The domain focus for the program is cancer biology, with emphasis on the complex signaling pathways associated with the RAS or RAS protein. So we illustrate these pathways on the left in a human-created mechanism really centered on the RAS protein. Now, this mechanism was completed just prior to the start of the Big Mechanism program. And what we see on the right is progress achieved under the program for machine-created mechanisms that greatly amplify what the humans have done. To the point we have such rich detail, we can explore a number of different possible intervention paths for pharmaceutical drugs really to address the challenge of cancer. So it is clear that we've reached the point in science where machines have very prominent roles in helping us solve problems of ever-increasing complexity. So we have a program actually to help us make sense of complex events by overcoming the noisy, conflicting, and potentially deceptive nature of today's data environment. This program is Active Interpretation of Disparate Alternatives, or AIDA. AIDA aims to create technologies for mapping and aggregating different pieces of information automatically derived from multiple sources into a common semantic representation or storyline, and then generating and exploring multiple hypotheses about the true nature of events, situations, and trends of interest. The program also hopes to determine a level of confidence for each piece of information and for each hypothesis that is generated. Now, I'd like to emphasize that this program does not take the human out of the sense-making loop, but augments the human's ability to keep track of multiple interpretations and not fall into the trap, as shown in the upper part of the chart, of one single interpretation that could be wrong or heavily influenced by disinformation. Wisdom, or sound judgment, is the next frontier, and it is one that we do not currently see as being within the reach of machines alone. We take seriously the importance of sound judgment because decisions can have life or death consequences. And so we see human-machine symbiosis as the key to the complete spanning of the data wisdom spectrum, which harnesses the complementary powers of machines at the lower end of sapience and of humans at the upper end providing wisdom or sound judgment. Equipping machines with more human-like communication and reasoning capability will make it possible for humans to more effectively correct machines as they interact and cooperate on tasks, and thereby open the door to stronger symbiotic partnerships between people and machines. We are looking at quantitative measures of the collective intelligence of all human teams. These measures can be used to design tests and teaming strategies for groups of cyber operators, as an example shown in this chart. But in the future, these teams will include intelligent machines. Cyber is a harbinger of this emerging partnership, and so we feel it is important to understand how to select, organize, and manage human-machine teams to optimize their collective intelligence and mission performance. Our Communicating with Computers program aims for symmetric communication between people and machines, or computers, where a computer is not there to merely take orders, but to be a partner, able to collaborate across a range of natural interactive modes such as language, gesture, or facial expressions. People really exchange complex ideas very efficiently by using ambiguous words within a shared context. Let me give you one example. A person picks up 3 wooden blocks, leaves a 4th block on the table, and then proceeds to stack these blocks one on top of each other. ABC, as we show here in this chart. This person then turns to another and says, quote, add 1 more, unquote. People really get this effortlessly, but today's computers would truly fail miserably. The Communicating with Computers program is looking to make it possible for a computer to talk with a person like 2 people do, in which an ambiguous phrase like add 1 more is understood by the computer within the context it shares with its human partner. Providing machines with common sense reasoning so that they can respond intelligently to new and unforeseen events and circumstances has been a long-standing goal for AI. We are exploring how to make it possible for machines to acquire a common sense reasoning about the physical world. For example, about gravity, friction, the fact that objects occupy volume or space. For humans, the acquisition of this reasoning begins at birth and is absolutely fundamental to functioning in this world. So in the chart, we show a child at play. I'd like to think that the child's focus on the ground is indicative of a decision based on common sense. Better to descend than to climb further and risk falling from that rickety tower of crates. So it is clear that machines would benefit by acquiring a common sense reasoning at least approaching that of the child's. Well, let me come back now to Symbiosis Homo et Machina. We are already collaborating with machines on data, information, and knowledge processing tasks. And technologies are emerging that will make it possible for machines to generate explanations essential to understanding by humans. In parallel with the climb of machines up the data wisdom ladder, technologies are being developed to ensure trust, which will ultimately include the trust of the machine in its human partner, as well as the trust of the human in the machine. We are excited about the next challenge of machines capable of common sense reasoning, sound judgment, and other levels of wisdom, as these are the keys to a true symbiosis between Homo sapiens and the emerging Machina sapiens. Thanks.